Okay, let's get started. So, are there any questions since last time? Yeah.
So the second question the assignment asks, part of it is to verify the covering array from the reduction of the covering array. So does that imply that we have to generate the entire covering array?
Yeah, you have to generate it yourself. It's just you don't have to present it all in your solution. So you can just save it to a file or something. Other questions? Yeah.
So basically for percent input file,
Sorry, yeah.
So for the input file numbers, you can just tap it and just generate an array and then import it.
Yeah, you can just read the file like with Python. You can just open the file and just read the lines of it. Yeah, there's no specification on what language you have to use or format. I just don't care. What I care about is can you actually verify if something's a covering array in whatever language or any format you want. I mean, you guys aren't freshmen. I'm not going to baby you around. You have to use this language. You have to use this format. No, you just use whatever tool that you're most comfortable with. Other questions? Okay, so I want to go back to the stuff we talked about last time. So last time, remember, we introduced this idea of a mixed level covering array, and then got a covering array from that, which is the uniform case right here. So we looked at an example here, and we quote-unquote verified that it's a covering array, even though we didn't really. We just did two sets, one set of two columns, and we noted that there are 9 other two sets that we needed to verify. I'm just assuming that you know how to actually verify the other ones, and I claim that it's a covering array. One thing that I want to rectify is this line right here. So this line's actually wrong, and it's my mistake. So can anyone tell me why it's wrong? So it says the last example, which is the mixed covering array on the previous slide, which had 2 columns with 3 symbols, 3 values, and 3 columns with 2 values, and we had 9 rows on that. And it says that because of the 2 columns with 3 values, we noted that because it's strength 2, T is equal to 2, 3 times 3 is 9, so therefore we must have at least 9 rows. But in the mixed covering array we has 9 rows, so there's no possibility we could have done better. And that's something we talked about last time. So why is it wrong if I said every column has 3 symbols? The last example shows that this is equal to 9 if we have every column have 3 symbols. Why is that not true? Not necessarily true, at least. If I have more symbols in each of the columns, can I have the same number of rows or fewer? Or at some point, do I have to have more rows? If I have more symbols. So let's look at this. Let's look at the mixed covering array here. Let's just say that I'm going to change the first 3 to a 4. What is the minimum number of rows I must have now? Strength 2. It is what? What is it? Yeah, 12. So if I add symbols, that does not imply that I can have the same number or fewer. And in fact, in this case, you actually do need more. So I'll rectify this. I'll upload slides again, but this is just not true. So if you thought that the last statement implied that the covering array number with 2, 5, 3 is equal to 9, that is not true. Okay. So we started to talk about why do we even want to consider covering arrays in the first place. So we noted that if we just look at this array, there is a parallel to how someone would test a real system. Each of the rows of the array corresponds to one test that we're going to run. And how do you actually run the test? Well, you look at each of the components in that one row and look at the value that's assigned to that column, and we assign those values when we do the real test. So for example, the mixed covering array we have here, where we have all zeros on the top, well, whatever corresponds to 0 for the first component, we're going to take that value. So if it corresponded to, I don't know, operating system, and 0 corresponds to Windows, then for that test, we'll use Windows. And then if 1 was Mac, for the tests that have a 1 in the first column, we'll work with Mac. And similarly for the other columns. And what you do is you run the test, and if it produces the result that you expect, the test passes. And if it doesn't produce the result you want, the test fails. Pretty simple. So either the test passes or it fails. We're not going to be focused on, unless you want to do it for your project, what the actual outcome is, producing the outcome first and testing whether the running the test produces the expected output. We're just focused on the array for now. And what we are guaranteeing in a covering array is that every interaction is tested. That's what a covering array is defined to have the property. It's guaranteed to test every T-way interaction. So the mixed covering array we had before tested every two-way interaction, but in general, if we're working with strength T, it tests every T-way interaction. We noted the sparsity of effects that we're going to assume, which is basically the assumption that if a fault arises in a system, then it's only the result of a few components interacting at the same time. It's not some giant conspiracy among a whole bunch of components at the same time. It's only a small number. So then we ended up here. So, of course, there are going to be some practicalities that we're going to look away from for now. We will come back to these later. The reason for that is we want to work with a simple model first. So for those of you who have taken 304 before, did you start with DFAs first? Or did you start with something else? Everyone trying to forget 304, right? Well, in 304, at least the way I'm teaching it now, we start with the simple model first, and then we work our way up to the Turing machine model, which is, if you have not taken it, it's the more complicated model. So same thing here. We're going to start with the uniform one, which is the simplest one, and then work our way up to incorporating some of these practical things. So mixed level, of course, some components don't have the same number of values that they can have. Rows that must be included. So there are some tests in some systems that you have to run no matter what. So in generating the covering array point of view, we don't even need to consider those rows. So therefore, we can just throw them out and work with a smaller set of interactions we need to work with. Instead of working with every possible interaction, we just work with a smaller number. There are some interactions that don't have to be covered, whereas in the usual definition, they have to be. So avoids is just, you don't have to do this if you don't want to, but if you do, that's fine. But for constraints, there are some interactions you absolutely cannot possibly have. Maybe there's some kind of danger in having that interaction there. Variable coverage. So if you want a really cool project, this is the one to actually focus on, because there's actually a lot of work starting in the last few years about focusing on variable coverage. And what does this mean? This means instead of having T-way interactions across the board, we have, okay, a two-way interaction for these two components, a three-way interaction on these, a four-way interaction on these, So it's variable depending on which components you want to actually test. Maybe some components you need to have a higher strength of testing for those ones, and some you don't need as high of strength. So there's been a lot of work there, and there's actually been a lot of work on this last one too, especially the first one, which is fault location. So a covering array doesn't actually tell you, hey, these two components cause the fault in this system. It just tells you there is a fault in the system. So you may want to think, okay, well, if there is a fault in the system, I want to know what it is. How do I identify which one it is? So you can actually try to do this with covering arrays in some sense. So let's go back to the example that we have. So let's just say that, it's getting quite crowded here, I guess. So let's say that the first test passes, the second test passes, the third test passes, but unfortunately the fourth test fails. Okay? And let's just say, for sake of argument, that every other test passes. So it's just the fourth test that failed. So what can you actually tell me? So what are the interactions that could possibly cause the fault here? Well, if it's an interaction that is not in that fourth row, could it have caused the fault? No. So any interaction in that fourth row could be the culprit here. So you could try to reduce your search space and say, any interaction in here, in that fourth row, I'm just going to look at those ones. So instead of focusing on every single one, let's just focus on the ones in the fourth row. And that reduces the workload you have to do, but it doesn't identify exactly which interaction caused the fault. So there's been a lot of work in trying to figure out, if I have some type of array, how do I guarantee to identify what the interactions causing the fault are? How do I identify them precisely? Okay, so there's been a lot of work there. And I think we'll, at some point, I think it's in the schedule, that we will talk about this a little bit. But okay, any questions on practical things? Yeah. Mm-hmm.
Possible combination inside that one test. It doesn't necessarily have to be two values. It could be 2, 3, 4, all of them.
Right. So that's also something that we would need to consider. That the strength that you have to choose is very important. So maybe it could be a 3-way interaction instead of a 2-way one, and we don't necessarily know. But if we do have a profile, as it's called, of the tests passing and failing, then whatever interaction it is, it must live in that fourth row. But if we have multiple tests that failed, then it's actually a little bit more complicated. Because now it could be an interaction that just happened to appear in both of them, or it could be two different interactions, one that appeared in one and one that appeared in another. We don't know necessarily. So it's just given a particular strength, can we identify a fault according to what test passed and failed? So the choice of strength actually is very important. So we will talk about that eventually. There is a paper that we probably will read, which is about trying to find what in the 802.11 spec for wireless communication, what they wanted to find out was, what are the components of the spec that had the biggest effect on transmission delays? So if we try to send like a packet or something over the web, and we change various parameters of the Wi-Fi signal or the network signal, what are the things that cause the biggest effect? And they basically just tried to find the fault, which is actually the thing that caused the biggest effect in that case. So yeah, the strength is actually a very important consideration here. But We'll just assume that we know what strength we actually want overall. Yeah, any other questions? Okay, so I was gonna spend more time on these applications, but I'm just gonna spend a little bit of time because I wanna move on to actual covering array stuff. So this first application, so you may think covering arrays are just used for testing. And that's it. They're only used for testing. They have no other applications. Well, I would say that that's actually a pretty important application, but it turns out they have other applications too. So you may want to figure out if you are doing anything hardware related, you may want to check if a circuit is actually valid. So if it actually does the right thing, you may want to actually test for that, of course. What we're going to assume for this case is that we don't know the internals of the circuit. We can't just assume anything. So any of the possible inputs we may need to test. So if we use a binary covering array, which means that it only has two symbols, 0 and 1, well, we can just feed those rows of the covering array over and over and over into the circuit. And if we assume that we have a faulty component, which means that if we change at most t pins, basically change a 0 to a 1, 1 to a 0, then it will be detected that there's a fault there. So if you look in the literature, the hardware designers are actually looking for some function called t-surjective. So what this means is they were looking at, instead of looking at the rows of an array, they were looking at the columns of an array instead. And it turns out that they were developing these beautiful results on their own, something called t-surjective codes, and the software testers were looking at things called covering arrays, even though they turned out to be exactly the same thing. So if you look, you'll just see t-surjective codes, but it means covering array. It's equivalent to a covering array. So this is, if any of you are in hardware testing, anyone in hardware related to anything? Okay, well, if you happen to like anything hardware related, so covering arrays aren't actually used for this anymore, and here's the main reason. So what hardware testers actually want to have is something called exposition. It's not something in storytelling, but exposition is actually something really important in hardware testing, which is I guess a pin is fine, that is quote unquote unknowable. So we may think of a circuit at all points in the circuit having a value of either 0 or 1, but there may be some places where in the circuit where we just absolutely cannot read what the circuit has. It could be a 0, it could be a 1. There's no way that we can actually tell ourselves. So if you are interested in that sort of thing, you may want to, for your project, look up something called X codes. So the X here means that there's something on the chip that we don't know the value of. So 0 means that it's off, 1 that means it's on, X means I don't know what the value is here. Okay. Yeah. So if you're interested in that sort of thing, look up X codes. Okay. So second application. So this one's actually really interesting. So I'll spend a little bit more time on it. So in the 1980s, people were really interested in how do we parallelize programs efficiently. So if we have a program, instead of it running serially on a computer in order, how do we parallelize it efficiently? So what people were looking at is something called a hypercube for doing parallel processing. And how many of you have ever heard of the hypercube? Okay, so a few of you. So unfortunately that this didn't catch on because people in sci-fi films can say, go compute this on the hypercube. Wouldn't that be like the a very catchy phrase in sci-fi? Go compute this on the hypercube. So what is this? So what we're going to do, so I'm just going to show a simple example. So we're going to list all of the 8 binary vectors of length 3. So what we're doing here is the Boolean hypercube. So I'm just listing all 8 here. And what we're going to do is we're going to make a graph. How many of you have not heard of a graph before? You probably all should have because you took 290. Okay, so what we're going to do is we're going to make a point, a vertex for each of these 8 vectors. And what we're going to do is the edges in this graph are going to be formed between 2 vertices that differ in exactly 1 position. So 0, 0, 0 is going to be matched up with 0, 0, 1. Where else is 0, 0, 0 going to be matched up? If it differs in exactly 1 position. 1, 0, 0, so it's going to be matched to that one. What else is it going to be matched with? 0, 1, 0. Yep. Because it differs in exactly 1 position. Let's just do one more example. Let's do the 1, 1, 1 at the bottom. So where is it going to be matched up with? Yeah, so 1, 1, 0, so that's going to be matched there. Where else is it going to be matched? 1, 0, 1, it's going to be matched there. And what's the other one? 0, 1, 1. And you can fill in all the other edges. But basically what you're going to form is something that looks like this. You're going to actually form a cube here. So if you, let's actually just do this. So 0, 0, 0 is here, 0, 0, 1. Let's see, 0, 1, 0, 0, 1, 1. Let's see. Okay, I can't actually think about like so, but you could put the other 4 on there. So what I want you to notice here is what is the diameter of this graph? By diameter, I mean what is the longest path between any 2 vertices? Longest, shortest path. So among all shortest paths between any pair of vertices, what is the longest one of them? 3, right? Because to get from any binary vector of length 3 to any other binary vector of length 3, you have to change at most 3 of the zeros or ones along the way. Maybe fewer, but at most 3. So by k cube here, we mean binary vectors of length k. So how many vectors are we going to list if we have k dimensions instead of 3? How many vectors are there of length k, binary vectors? 2 to the k, right. So the number of vertices here is 2 to the k. What's the diameter of this graph? If we have the k cube instead of 3. K, exactly. So another important thing, what is the size of the neighborhood of any vertex, the number of neighbors for every vertex? It's also k. So this is actually not v. Number of neighbors is also equal to k for every vertex. So this is actually a pretty remarkable graph because it has a lot of vertices and it has really small diameter, logarithmic diameter in the size of the graph. And it's actually, it only has a very small number of neighbors overall. So what people wanted to do was if we wanted to do computations on this thing, well, if we needed to transmit information from one vertex to another, the diameter is small, so the time to send something from one processor to another is very short. But here's something also interesting. So we want to have a cube when we're doing computations. Instead of having like a face here and a face here, so instead of having something like this, so no edge going across here, so I have two faces instead of the whole cube here. This is obviously less advantageous than the whole cube because there's no connection between the two faces. So why do we want a cube? Because we don't have to send information from far away vertices to other vertices, even though the diameter is small. So what we wanted to, what people wanted to figure out is how many vertices can I delete so that I still have an operational cube of a certain size. So like for the 3 cube that we did down here, if we delete one vertex, we still have 4 vertices in a cube working together. If I delete 2 vertices, well, I could delete, say, 2 opposite corners and I don't have a face anymore. So people wanted to know, well, if I delete a certain number of points, how big of a cube can I still have remaining optional? So you may be thinking, okay, well, why hasn't this caught on? And the reason is that if we look at the probability of specific vertices being deleted in a certain order, then that actually is astronomically low, that those particular vertices are deleted. But what people wanted to know instead is, what is the probability of still having a cube? Not that a particular set of vertices are deleted. But the original question was based on how many rows does a covering array have? So I put it here, but basically, if you know the optimal size of a covering array, you know the minimum number of points that have to be deleted so that we have an operational cube. Okay. Qualitative independence. So I won't spend much time on these, but so how many of you have taken linear algebra? So you may have heard of something called linear independence. So linear independence, I'm just going to give a short summary on this. Linear independence is focused on understanding how much something is expressed. How much does a particular effect have on a system? Whereas with qualitative independence is about whether the effect actually is there or not. Linear independence is about how much does it affect the system. Qualitative is whether it's there or not. That's all the difference is. It's a generalization of linear independence that Renyi was focused on. How many of you have ever heard of the Erdős-Renyi model for graphs? Erdős-Renyi. One person. Awesome. Yeah, so Erdős and Renyi formalized the notion of random graphs in a certain sense, and this happens to be the same Renyi. So I won't talk much more about that. Design of experiments. Have any of you taken design of experiments or statistics? Okay, if you've never heard of this term, then we'll just skip it. But it has applications there as well in terms of qualitative independence. So some other applications, I won't spend time on these very much, but the first one's kind of interesting. Covering arrays have applications in machine learning. How many of you are interested in machine learning? So if you want to find a sparse classifier for computing something, some function, where you don't know anything about the function, it turns out that the optimal queries that you send to the classifier are those of a covering array. So there are many, many other applications other than testing. Those are the things I want to um, have you at least realize. Any questions on applications before we move on to real stuff? Okay, so let's move on to basics of covering arrays. So what we're going to do here is we're going to talk a lot about the model that we have developed. So a covering array where we have a certain number of rows, a certain strength, a certain number of columns, and every single column has a certain fixed number of values. So remember that we're dealing with CA, N, T, oops, can't get these out of order, TKV, where N is number of rows in the array, K is the number of columns, V is the number of values, and T is the strength. The number of columns that we look for all of the possible interactions at a time. So the example we did a while ago had T equal to 2, but working with general T here. So we're going to actually do quite a bit, not in this set of slides, but over the next few weeks, which is, well, how do we actually make these things? So computational constructions, that's probably the thing I would focus on when you're starting to think about your project, because there's a lot of work in computation that hasn't actually been done yet. So, and it's actually really easy to start getting into that space. We'll look at asymptotics. So if we talk about a very large number of columns, what happens to the size of these things? And it turns out we can precisely determine what that is asymptotically. But sometimes we can get direct constructions. We can just say, here's a simple procedure that will generate the array in one swoop. You don't have to do any computation on a computer. Here's the simple procedure. And then recursive constructions, it sounds really intimidating, but the whole idea is you have a bunch of covering arrays or some other objects, and then you glue them together. That's all it really is. So it's recursively working on smaller arrays. That's all it means. Okay, so let's first talk about lower bounds. So in general, we don't know the exact number of rows for covering arrays, and we'll see that. But if we don't know the exact number, what people want to do is, here's a lower bound and here's an upper bound, and the true answer must lie in between them. So we want to maybe just figure out what is the fewest number of rows that an array could possibly have. So let's first talk about the mixed case. So if I have values v1 through vk, so in the first column, let's just say that we have an array that looks like this. So there are v1 values in the first column. There are v2 in the second, v3 in the third, etc., up to vk. And maybe we don't know like which one's the largest one or whatever, but let's just say we have this. Why can we assume that all of the vi are at least 2? Well, can any of the vi be 0? No, because we can't put a value there if there are no values allowed. But what if one of the vi's was 1? There's only one value in this column. Does that impact anything? No, why?
Because it doesn't change. We're always testing it.
Right. So if we have a t-way interaction that involves that column, well, it's always going to have that one value in every single row, because if one of the vi's is 0, then we can just say, oh, well, that column already has that value, so we don't even need to worry about that column. We don't have to make a choice about what to put there. So what we can say here is, if there is an MCA NT V1, and let's just say at Vi minus 1, at Vi there's a 1, so at the ith position, at the ith column, or wherever in this, there's a 1, then what we can do is just scratch out that column. We don't need it anymore because it's always going to have the same value throughout. Then there exists an MCA on the same parameters, but without that 1 there. Okay? Yeah, because that 1 column has to have the same value everywhere. So because it's an MCA, every single interaction involving that column must be covered, must be there. So because there's only 1 value. Okay, so now we're just assuming that every single column has 2 or more values in it. And we can't do the same trick with 2 because now we have to have a choice of whether it was a 1 or a 0 or whatever. So why can I make the third statement where the number n, the number of rows, must be at least the product of the t largest VI symbols? Why can I assume that? Well, look at those T columns, the ones that have the largest VI. Well, all of the interactions in those columns have to be there. So that means that the number of rows must be at least that number of interactions. So think about the earlier example we did, where we had the 2 columns with 3 symbols in it, and we had T is equal to 2. Well, 3 and 3 are the largest number of symbols in the whole tuple we provided. So 3 times 3 is 9, so the number of rows we need is at least 9. So let's actually revisit that example shortly. So let's just say that we have the exact same example again, except now I'm going to say that the strength is 3, not 2. But all of the other parameters are the same. What is the minimum possible number of rows now? Well, how did we find the 9 when strength was 2? We looked at the columns 3 and 3 because those were the largest ones and determined it was 9. What about now? Now, look at the 3 largest column values. What are they? 3, 3, and 2. So what is the minimum number of rows? I know you guys can multiply, okay? So 3 times 3 times 2 is 18. So this 9 we can say is not true. So if we have the number of rows n here, whatever that is, it might not be possible to get 18. We know that n must be at least 18, no matter what. Does that make sense, or do you want me to go over that again? Okay. So all we're really doing here is just figuring out what the minimum possible number of rows. We're not determining the exact value. We're not trying to get a better estimate. We're just doing the absolute minimum number of rows possible. So why can I say then that the covering array number, where we have the same number of values in every column, why is that at least v to the t? Well, it's the exact same idea. Pick the t largest number of symbols. the T columns with the largest number of symbols. Well, doesn't every column have the same number in this case? I need more enthusiasm than just the one over here. More heads nodding? Okay. So if every single column here has exactly V values, well, if we pick any T of them, then we must have V times V times V times etc. times V rows. So if we pick T of them, that means we have V to the T number of rows in general. So let's just do one example. So if we have can of 2, 5, 10, this is actually a very famous set of parameters here. And we'll talk about that in a few slides. What must this be larger than? Or at least. 100, yeah, because it's just look in the value in the third position, take it to the power of the number in the first one. Nothing complicated. So it's at least 100. Okay? Any questions on that? Okay, so the question is, of course, can this be realized in general? Can we always get the minimum number of rows? And if so, great, we know the answer all the time. Unfortunately, well, the class would be over if this were true, so it turns out we can't. We can't actually get the minimum number in general. So, and actually this parameter set is one that we actually don't know the answer, but I'll talk about that in a bit. So we're going to show that can of TKV, the covering array number, grows asymptotically. So it can't be V to the T for all K. So if I make the number of columns larger and larger and larger, then at some point we're going to have to break through the V to the T barrier. And it's just the number of rows has to go up and up and up. But the question is, of course, what is that growth rate? So yeah. So what we're actually going to show, not in full today, but we're going to show that can of TKV is big theta log K for fixed V and T. Anyone not know what theta is? Or big theta, at least. Big O notation. Okay, so hopefully you all know that. So, but we'll show this in several stages and in several ways. But if I tell you the number of symbols and the strength and fix those so that they are constants in some sense, then what happens to the growth rate of can TKV? If I make the number of columns large, it turns out to be logarithm in K. So if I have like a billion columns and I try to contrast that with a trillion columns, then if I try to plot that, it would look like a logarithm curve. That's all I'm trying to say. Okay, so it's just some constant times log K. Okay, we haven't shown that, we will show that. Okay, so let's look at this second statement right here. Every covering array with some strength T, it doesn't matter what it is, as long as it's at least 2, it is a covering array when I fix the strength to be 2. So if I have a covering array with strength 10 or 3 or 5 or whatever, then I claim that the same array is of strength 2. Why am I justified in saying that? So let's actually do an example. So let's look at the case when t equals 3. So let's just say that we are looking at all the 3 tuples in 3 columns. So here's one column, here's second column, here's the third column. And I'll give them names, C1, C2, C3. And we have a test here, test here, test here, etc. And I claim, and maybe there are other columns, I don't know, but let's just say that we're looking at these three. Well, look at the first two columns. Doesn't every single pair have to appear in those two columns? Maybe let's make it more concrete. So let's look at the binary three vectors. It's getting me again. Let's do this. Who else loves notability? I love notability. Okay. So here are three columns. And all of the 8 binary vectors are here. So now I claim that the same array, those 8 rows and 3 columns, is also a covering array of strength 2. How can you be sure? Without even looking at the array, how do you know for sure? Well, let's see. Look at the rows where 0 appears on the very last column. On the third column, look at the rows where 0 appears. What can you see? On the other 2 columns. Maybe I'll highlight it. What do you see over here? Oh, all interactions of those first 2 columns appear. What if we check the first and third column? The same is true. If you look at the second and third column, it's always true. Here's why we can assume this. Well, take any t-way interaction, or any t columns, I guess, and pick any 2 of them. Well, among the other t minus 2 columns, all interactions have to appear because the original array was a covering array. Every t-way interaction appears, so if we look at every 2 columns, every t minus 2 way interaction has to appear alongside those 2. So since we looked at every possible 2-way interaction and every t minus 2-way interaction, therefore, every covering array of strength t must be one of strength 2. So the only reason we're going to do this is establishing a lower bound. The only reason we're doing this. Okay. Any questions on that? If you don't get it immediately, I would highly suggest actually working through an example, a concrete example yourself. Okay, so now let's look at the third statement here. So supposing that we do have a covering array of strength 2 now I claim that we can reduce the number of symbols to 2 everywhere. So why can we assume that? So this one's a little harder to see, but it's actually pretty simple too. So I'm going to move this over. So suppose that we have 2 columns here, but I'm going to have 3 symbols. Okay, 2, 0, 2, 1, 2, 2. And I want to have only 2 symbols, 0 and 1. I want to get rid of the 2. What could we do? I want to have the same structure of the array, and I don't want to change any of the 0s or 1s. I just want to change the 2s to either 0 or 1. Does it matter what I change them to? Let me help you. Let's take out every single 2, and I'm going to change them to stars. So we'll introduce what star means, but star we will interpret here to mean it doesn't matter what the value is. It could be either 0 or 1. So let's see. So star, star, and double star. Well, among these 2 columns are all interactions appearing. of zeros and ones? Yeah, because they appeared originally, so they must appear now. Because I didn't change those, I didn't change the zeros or ones, I only changed the twos. So for that reason, we can assume now, or at least every covering array with any number of symbols must be one with two symbols. Okay? And I think we're out of time, so I'll see you on Wednesday.